we're going to very briefly talk about how we predict drag and lift forces on objects in engineering. Now we all know that a body that's moving through a fluid experiences some force. We divide that force into two components based on its direction. The lift force is perpendicular to the flow, and the drag force is parallel to the flow. And then the drag force has two components of its own. The first is skin drag, which is due to shear forces, basically the viscous forces on the surface of the object. And then the form drag, which is due to pressure differences between the front side of the object and the back of the object. Now, this is pretty difficult to model analytically. We talked about how potential flow theory predicts no drag, and that gave rise to D'Alembert's paradox. The Navier-Stokes equations are very difficult to solve. And even in this case, boundary layer theory comes up short because we can see boundary layer separation and turbulent wake formation. So even boundary layer theory makes it difficult to analyze. So because of this, we typically use empirical methods. We collect a lot of data and we correlate it and come up with some function. Modern analysis also uses CFD very frequently. This type of behavior is very important in sports for things like the flight of a golf ball or the performance of a racing car. It's also important for the aerospace and automotive industries, so the state of the art is advancing pretty rapidly. If we look at bluff bodies, boundary layer separation becomes very important. On the front of the body, the pressure is decreasing as we move around it, and that's promoting the boundary layer to stay attached. And so inviscid flow theory actually works pretty good on the front side of the body. We can see from the graph that the inviscid flow theory matches with experimental data pretty well. However, on the back side of this body, we have an adverse pressure gradient. The flow is slowing down as the streamlines get further apart, and so we have a pressure increase in the flow direction, and that promotes boundary layer separation. And when the boundary layer separates, it creates this turbulent wake, and because the wake is turbulent, the pressure everywhere is reasonably constant. So we have this region on the back side of the object where we have almost constant pressure, and it's significantly lower than the pressure on the front side. And so that gives rise to a drag force because this pressure is much lower than this pressure, so the pressure forces are pushing the object that way. Now, on the turbulent boundary layers have higher inertia, boundary layer separation is delayed, and so we have more pressure recovery. We have a smaller area here and a smaller pressure difference, so we have large reductions in drag force once the boundary layer transitions to turbulence. And we can actually see this in nature. If we look at sharks, shark skin has dentins, small tooth-like projections, which is why we can use shark skin as sandpaper in some cases. But the actual function of these dentins is actually to promote turbulence. And what that does is delays boundary layer separation on the body of the shark, reduces drag, and that allows the shark to swim faster and reduces energy consumption when it's swimming. So that's kind of a neat application for tripping a boundary layer to turbulence. So we can look at this method and we collect a whole bunch of measurements and plot drag coefficient as a function of Reynolds number. And we can get a graph like this that we can use to predict the drag force on a cylinder. So this just shows a graph like that, and you can note the significant drop that shows up at around Reynolds number of 500,000. That's where we see the transition to turbulence. So once we transition to turbulence, the boundary layer separation point moves back, drag coefficient drops very quickly. If we want to find the drag coefficient, all we have to do is calculate the Reynolds number, draw the vertical line to see where the value of this graph is, and then draw the horizontal line across to read the number off the vertical axis. Now, it's important to note that we have this long region where the drag coefficient is almost independent of Reynolds number. It's almost constant. And this is because the drag coefficient here, the drag force, is almost entirely due to pressure forces, or form drag. We'll talk about that a little bit on the next slide too. Now we can extend our 2D analysis to 3D and look at spheres. So that's what this graph is showing. Now on this graph there's this theory due to Stokes. Well, Stokes' theory gives the shear drag for very slow laminar flows, where Reynolds number is approximately equal to 1, or 10 to the 0 on the graph. There's no boundary layer separation. It's only due to viscous forces. It's important to note that this component of the drag force decreases very rapidly. In fact, once the Reynolds number gets to be above 10 or 20, almost all of the drag force is due to pressure forces rather than shear forces. It's also important to note the subgraph here, where you can see the change in behavior between the smooth sphere, which is what's graphed on the larger graph, and a rough sphere, and then the dimples on a golf ball. So it's kind of neat that the dimples on a golf ball exist simply to transition the flow on the front of the ball to turbulent flow. What that does is delays boundary layer separation and reduces the drag on the dimpled golf ball. When the drag is reduced, it increases the distance you can hit the golf ball. And there's a lot of money. Golf ball sales represent a lot of money, so there's a lot of money in making better golf balls, and that has resulted in a lot of drag force and lift force analysis with different methods over the years. This transition to turbulence can also stabilize local fluctuations. As an example, we can look at a knuckleball in baseball. Now, when the knuckleball is thrown, the boundary layer is laminar. However, the laces on the baseball represent roughness elements, and as the knuckleball very slowly rotates, those roughness elements trip the boundary layer to turbulence at a location that varies with time. So as the ball is flying, it has this very unpredictable transition to turbulence. And what that results in is drag and lift varying widely as the ball flies through the air, which gives it an erratic flight path. It's very difficult to hit. It's also very hard to throw because of the increased drag. It decelerates more quickly. So it requires some adjustments to the throwing method. And what happens is, in the mind of the batter, the brain is trying to predict where the ball is going to be rather than displaying in your brain where it is at the moment. And as the drag and lift force changes, the path of the ball changes, and the ball kind of appears to jump around because your brain is predicting different locations for where it's going to be in the next few instants. We can also look at other types of bluff bodies. The graphs shown here are objects that have sharp corners. And so in this case, boundary layer separation is going to be at the location of the sharp corner. It's going to be almost independent of Reynolds number. And in this case, the drag is almost entirely due to form drag. So as long as the Reynolds number is greater than about 1,000 or so, the drag coefficient is going to be almost constant. Now, we can't do this analytically. We talked about the difficulties. We can use CFD or other methods, or we can rely on experiment. And we have tables that show drag coefficients for various shapes under all kinds of different conditions. In many flows, we can see interactions with nearby objects. So we can look at drafting in racing, where the second car is inside the turbulent wake of the first car. This reduces the pressure force on the front side and reduces the power required to keep moving at a given speed. And that helps reduce fuel consumption, and so the car doesn't have to stop for pit stops as often, and so on. This is actually used in nature as well. It's why geese fly in an inverted V formation. The first goose sort of breaks the path and reduces the drag force on the trailing geese, so the trailing geese have to use less energy as they fly in formation. And then the geese will alternate which goose is at the front of the formation, so that everybody gets the chance to sort of take a break and fly within the lower drag region of the flock. We can also look at what we call fairing, or streamlining objects to make the rear side more tapered. What this does is it reduces the adverse pressure gradient and delays boundary layer separation. And delaying boundary layer separation helps us to decrease the drag. So we can use this on things like car mirrors and aircraft components to reduce drag by as much as 80% on those objects. A very simple version of fairing is a trailer tail, which you might have seen while you're driving down the highway. This is a relatively inexpensive addition to a trailer like this, and it can reduce the drag by 15% or more, depending on the design. And that's a big savings in fuel, which is translated to a savings to the consumer. In recent years, CFD has been used to optimize the front and rear contours of cars. This has allowed us to reduce the drag coefficient from about 0.55 to 0.3 or less, and in fact, it can be as low as 0.2 for some types of sports cars. And it's one of the reasons that many different brands or varieties of cars look very similar, because they've all been optimized to try to reduce the drag coefficient and reduce fuel consumption. Vortex shedding is also important. What happens is the formation of the turbulent wake results in occasional vortices breaking off from the wake and moving out into the flow. We call this a vortex street, and they happen on alternating sides of an object. The frequency of this vortex shedding depends on the Reynolds number. So you can see here we have these alternating vortices in the picture. The top one is an experimental picture of light refraction, and the bottom one is actually an island. You see an island at the head of the vortex street, and the vortices that show up in the clouds as the wind moves past the island. So as we said, the frequency depends on the Reynolds number and creates an oscillating lift force. So if we take this object and we attach a force sensor to it, we can measure the frequency of the oscillating lift force, calculate the Reynolds number from that, and use the Reynolds number to find the velocity of the flow, which is a pretty important application. These types of oscillations, however, can also cause high structural stresses and become dangerous. The YouTube link on this slide shows a video of the Tacoma Narrows Bridge, which was built, and then the wind started to create these oscillations, and the whole bridge basically shook itself apart. I would recommend watching the video to get some idea of the importance of this kind of behavior. Now we can reduce this kind of behavior by adding roughness elements. That helps stabilize the flow, increases its inertia, and reduces the frequency of vortex shedding. We also want to talk very briefly about the lift force. Now the lift force is related to the planform area rather than the projected area. So we have a drag force for a bluff body where we use the projected area from the front of the object. However, when we're looking at the lift coefficient, we look at the planform area, or the area of the plane parallel to the flow. Okay? And then we have alpha, or the angle of attack, which is the angle between the freestyle flow and the airfoil angle. It basically, the angle of attack determines the circulation of the flow around the object. So the lift is created essentially from in-viscid flow analysis, Euler's equation. Essentially the air on top of the wing is moving faster than the air on the bottom of the wing. Therefore, it has reduced pressure, and that pressure produces a force that moves upward. So it's basically generated from circulation of the flow around the object. Now, computers can actually be used to design airfoils more efficiently by adjusting the shape to control the pressure difference. And we can do that by simulating different types of airfoils rather than building them and making experimental measurements. We can also use this in other applications like Formula One race cars, where the front and rear airfoils and the underbody diffuser is designed to create a downward lift. And the downward lift actually can produce up to 5 Gs of downward force at maximum speed. What this does is it helps improve traction. There's more friction between the wheels and the ground, so you can take turns more quickly, and it helps improve the stability of the car.